In this video, we're going to go through a basic overview of redox titration. We'll look at setup theory, and then we'll do a simple calculation just to walk through the process of the analysis. We're going to start by looking at the overall setup of a titration and talk about some of the theory involving endpoints in a redox titration. So just as a reminder for terminology, in a redox titration, we're still going to use a burette to hold our titrant. And we'll often use an Erlenmeyer flask to hold our sample. The reason that we'll use an Erlenmeyer is it has a very narrow neck, and so we can swirl the solution in there without worrying about anything splashing out. Our burette is going to be graduated, meaning it has volume markings down the side. These allow us to determine how much volume is in the burette and how much has been added to our sample. When we looked at acid-base titrations, we often used acid-base indicators to determine when the titration was done. And there are redox indicators, but we can actually use selected oxidizing agents and reducing agents that have inherent color changes to determine when a titration is complete. So if we look on page 7 in our data booklet, right away we can see two pretty good oxidizing agents that are really colorful. So I'm going to highlight our permanganate reduction reaction and our dichromate reduction reaction. And if we flip to page 11 in our data booklet, we can see that permanganate and dichromate have very distinct colors. So permanganate is a deep purple or a purple pink, and permanganate forms manganese 2+. And manganese 2+ is either colorless or a pale pink. And so we're going to see a color change if we use permanganate, in which we start at a dark pink, and as it reacts, it becomes colorless. In this case, the end point of our titration, that's the color change point when we know the titration is finished, is going to be light pink, where we have a little bit of extra permanganate in our solution. So we've added 1 drop more than we needed. If we were to use dichromate for our titration, dichromate is an orange color or a pale orange color. And chromium 3, which dichromate forms, is either green or blue-green. And because we're often diluting this down, if we start with dichromate in our flask, or in our burette, we'll see the dichromate is going to go orange, and then when it reacts, it'll look either pale green or colorless. And therefore our end point is going to be a very pale orange, where we have 1 drop too much of dichromate. And because we have these really vibrant colors, we're able to carry out these titrations without adding any extra indicator into our sample or our burette. All right, so we're going to look at a titration calculation. We're going to break down this problem and walk through step by step how to solve it. At the end of the day, this is just a stoichiometric problem like we would have done in Chemistry 20. The only new step is actually determining the balanced redox reaction. So we have a 20 milliliter sample of acidified iron 2 sulfate. So right away, we can start to pull out some information. So this 20 milliliter sample means that iron 2 sulfate is in our flask and not in our burette. So that's in the flask. And it's titrated with 0.026 molar potassium permanganate. So that word with that we see there That word with implies that our potassium permanganate, that's in our burette. And then we have our data collected during the titration. And so from this data, this is the volume of permanganate added until the solution turned a light pink. And we can see that there's these endpoints written here with the colors at when the titration was stopped. So in this question, we're being asked to find the concentration of iron 2 ions in the sample. Right away, because we know that we're reacting potassium permanganate and iron 2, we can probably determine what the reaction is, but it's always good practice to go through the 5-step method. So we're going to list everything that we have present in our flask and our burette. So at the moment we add a drop of permanganate, what's present before reaction? So we will have potassium ions from our potassium permanganate. We will have permanganate ions. Our flask is, and this is a solution, so we will have water. Our flask contains acidified. So acidified means H plus ions are present. The reason that we acidify the flask is if the acid goes into the burette, it actually is going to cause a spontaneous reaction of permanganate with water, which we don't want. So we want to keep the acid away from the permanganate as long as possible. We also have iron 2 plus ions and sulfate ions. So we can use the table on page 7 in your data booklet to determine our strongest oxidizing agent and our strongest reducing agent. So the strongest oxidizing agent here is the reduction of permanganate. So acidified permanganate ions are a very, very strong oxidizing agent. And this is the balanced half reaction. And this is directly from your book. You don't need to go through the steps of making the half reaction. Save yourself a little bit of time here. So that is our strongest oxidizing agent. Our strongest reducing agent is iron 2 plus. And iron 2 plus is going to be oxidized to iron 3 plus by losing an electron. So in order to carry out any of our calculations, we need our balanced reaction. So we're going to multiply the iron half reaction by 5, and we're going to multiply the permanganate half reaction by 1. So our net reaction is going to be permanganate plus 8 hydrogen ions. So we really just need lots and lots of hydrogen ions, plus 5 iron 2 plus ions, forms 5 iron 3 plus ions, plus permanganate, plus manganese 2 plus, and 4 water molecules. So in this reaction, we want acid to be in excess. So typically when these reactions are carried out, we add way more acid than we could ever need, just to make sure that there's enough present to react with the permanganate ions. Okay, so we have our net reaction. The next step is going to be to determine how much volume was added. So what was the average volume of permanganate? So we're going to go to the next slide with that, and I'm going to carry forward this reaction. All right, so our next step is going to be to determine how much permanganate was added in each of our trials. And we're going to do that by taking our final volume and subtracting our initial volume. These volumes are just read off of the burette. So 14.16 minus 0.00 is 14.16. 28.05 minus 14.16 is 13.89. 41.9 minus 28.05 is 13.85. And 13.8 minus 0 is 13.8. Now, the rule of thumb when we're dealing with titration is we only want to include data within 0.2 of each other. So only include trials that are separated by less than 0.2. So if we look at our data here, these three trials are all within 0.2. They're actually all within 0.09. This first trial, though, is outside of that range. And we can tell that it's probably not a great trial because the endpoint color is darker. So we're just going to ignore trial 1 when it comes to our analysis here. And we're going to average the volumes from the other three trials. So our volume of permanganate that was added on average is going to be 13.89 milliliters plus 13.85 milliliters plus 13.8 milliliters, all divided by 3 because there's 3 trials. And we get an average volume of 13.85. Now that's rounded. And I'm going to, when I do the math for the rest of the question, I'm actually going to carry forward the unrounded number. But I'll write the rounded number down there just for easiness. Okay, so we're actually now ready to solve this problem. We have our balanced reaction. We know a volume and a concentration for our permanganate, and we know a volume for our iron sample. So we're going to start this by solving for moles of permanganate. So how many moles of permanganate did we add? Because our endpoint is going to come when we have stoichiometric equivalent moles of permanganate and iron. So I'm going to start by multiplying the concentration of permanganate, which is 0.026 moles of permanganate per liter. And I'm going to multiply that by the volume of permanganate that was added, which in this case is 13.85 milliliters. Now I'm going to write that as liters just so that I can show the unit cancellation. So our liters here will cancel. Biggest mistake we see students make is we see students switch which volume goes where. So really make sure that you have an understanding of this. This is the concentration of permanganate. So this must be the volume of permanganate. These two numbers are a data set together. So all I've done here in this calculation, if you're a formula user, moles equals concentration times volume. And now I know the moles of potassium permanganate that were added to the flask. So that brings me to the next step. I want to find moles of iron that are present in the flask. So we're assuming that they're stoichiometrically equal, meaning if I multiply by the mole ratio, so I'll put 1 mole of permanganate on the bottom of this fraction of the bottom of the ratio, and that 1 comes from the coefficient here. So I put 1 mole of permanganate there on the bottom and 5 moles of iron 2 on the top. And that again comes from this coefficient here. The reason that I put the permanganate on the bottom is now my moles of permanganate are going to cancel. And so all I've done here is I've determined the moles of iron by taking the moles of permanganate and multiplying them by the mole ratio. So now I know how many moles of iron were initially in the flask before I started titrating. To find the concentration, I'm just going to divide that by the volume of the iron sample. I'm just going to put a 1 on top here. And we had a 20 milliliter sample of iron. So I'll put my 20 mils in liters there. And And so my final units here are going to be moles of iron 2 plus per liter, which is the units I want for concentration. In terms of math here, concentration equals chemical amount divided by volume. And so all we found here is the concentration of iron 2 plus. And that gives us 0.0900 moles per liter. And for SIGDIGs, we had 3 in the concentration of our permanganate. So we're going to have 3 in our answer here. So that's a typical redox titration question that you would see. In the next video, we're going to look at something called standardization, where we do 2 titrations back to back and use the information from the first to understand the second.